Okay, so today we're going to be talking about those stacks, and mainly what are they, why we need them, and how to use them. Now stacks are, kind of very documented how to deal with things, which implements something called the LIFO, which is a shortening of last in, first out. There are some situations where you would like to be able to have such a thing, like this kind of a pile of something, or like a set of CDs. This is called a stack because the first that gets in is the last to be out, but the last that was in is the first to be out. So that's the type of things that works like that, and it has some kind of advantages and some kind of usage, but let's talk about how this works first. Mainly, basically the main concept of a stack is that you can add things, take out things, but the problem is that when you add something and you add another thing, when you take out, you cannot take out from the middle or from whatever. The concept is that it should not allow you to take only from one place, which is the top. And then so when you put your your rack of the stack of CDs, you put them one next to the other, one on top of the other, but when you would like to take out, you're going to be taking out only the one on the top, and so on. So you can implement this in different ways, but let's talk about what we might need. So in terms of the operations. Now for a stack, what we could do, we could clear, empty it, ask if it's empty, push. This is what when you put something in the stack, and pop when you take the one on the top. And the top element, this gives you the one on top without taking it out. So without removing it, this top element will give you, okay, just tell me what's on the top without removing it from the top. Because if you just pop it, it takes from the top, but it also removes it. Yes? Yeah, this is an example. This is an empty stack. You push, that means you put 10. You push again, that means you put 5. You pop, you get it out. So when you push, you have to mention what's the value that you'd like to push. But when you pop, you don't mention anything. Pop is just like some kind of a method that has no arguments. It just gives you just whatever is on the top. And that's the thing. Now, why we use that? One of the main things is to check for the delimiters. Let's say you're writing something, like this, some kind of things. How does compilers, for example Java compiler, check that you're not missing a parenthesis, especially if you open one and then another one, like these nested ones, like here, for example, something like here. So you have to just pay attention as to when you open one and you open another one, when you close, you have to take out, you're closing the inner one. And this is kind of useful to check using a stack. And for example, how this works is that this is some kind of a pseudocode or for this, how to make the delimiters matching. So you're going to read something. Let me maybe show it an example. Like say we have something like this. This is the input. Now the first thing, you read the text until you find some kind of delimiter, which is you're looking for those ones. When you find these ones, you push them in the stack. So we're not interested in this s or the equals, but so it takes all this expression, takes it one character at a time, and then if it finds that this is one of those that have like opening and closing, then I push it in the stack. So for example, something like this. So I'm just going to discard this one. That's why you see the stack is empty. We don't put anything until we find this. Now when we find this, we take it out, and then this character is going to be pushed into the stack. Then there is this other one. Well, we're not interested in them, because now when we push, that means when we found these opening ones, we push. When we found the closing ones, we pop. So that's why we reach from until the end, from the beginning until the end. We read one character at a time, and then if we find these are the opening ones, we push them. If we find the closing ones, we pop. So now they put a condition that if we pop, the one that we pop do not match the one that we're expecting to pop, then we have some kind of a problem. So anyway, so we just keep pushing. For example, we push this one, and then when we pop, we check it out. When we find this one, we check it out, and then if we at the end of we finish all our text, and we find that something is still in the stack is not empty, that means we opened something that we never closed. And that's how we can. This is one way, one justification behind that, and so that's the main idea. And that's easier to do that with a stack. Without a stack, it's kind of, if you'd like to do some different ways without using a stack, it's going to be a little bit tricky. Another usage for the stack is that when you'd like to work with very large numbers. Now we know that in terms of the data types, we have the largest, let's say, integer is an int. Is a long. But what's the size of a long? A long can go up to, I don't know, let's say 4 billion or something like that. But what if you have a bigger number than 4 billion? You would like to have like 4 billions of 4 billion. I don't know what's the size of a, I'm just curious. Long data type, or maybe put Java, long size. Size max, something like that. Okay, so let's say these are the max values. So how many are, so this is just a billion. You have a billion of a billion, 9 billion minus 9 billion of a billion, plus billion, 9 billions of a billion, 9 billions of a billion. Anyways, now imagine you would like, this is not enough, because mashallah you have so much money that you exceed this limit. So you'd like to work with big numbers. Well, it's kind of hard because you're hitting the wall. The limit, the max you can use is the long. So does it mean that we cannot work with, for example, if we have some kind of formulas that requires to do some calculations for very big, very large numbers, we cannot do that? Well, yes, we can, but using a stack. That's the main idea. So how do we use a stack? Now let's say, well, imagine that these are very big numbers. Now we just show you a small example so we don't get lost with the huge number of digits. But let's say we have these big numbers to add. Now what we do is that you have 3 stacks. One for the first number, the other one for the second number, and the third one for the result. Now notice that the numbers, which one is entered first, is the 5, which is not the ones in the units, but the largest unit that we have. So not in the tens, the hundreds in this case, and the thousands in the other one. So we start by putting the ones from the left. We put them and we push them to the stack. And then we do the same with the other one. And then when we do the operation, we just pop one from each, and then we add it and we put it in the result. And then we pop again the next one. But what if we have, for example, a number that is above 10? It's 17. We're not going to be putting 17. So we take this 7, we put it here, and this one we remember it because we need to add it to the other one that when we add. So when we have this 5 plus 3, we add that one. Sorry, that's a 7 plus 5. We add it to 1, so it becomes 13. And then 13, we take the 3, put it in this result, and that one we add it to what's remaining, and then this is going to be the result. So the result is, but when you read the result, you don't read it the same way that you entered the values, because the result is kind of inverted, because we put the rightmost number first, while here we put the leftmost number first when we initialize the stacks. So now to read this is 4,376, while here we read this 3,784. But anyways, with stacks, you can find a way how to get around the limit of the data types that you have. And that's another implementation of the stack. So this is just to show you that why we need those stacks anyways, and they're kind of useful in these situations. Yes.
So we make stack 1 and stack 2 and then make a loop.
Make a loop and stack 3 as well for the result.
Stack 3 and then a loop.
Then you make a loop as long as it's not
If it's
empty.
bigger than 10, do something.
Yeah, it's bigger than 10, you just, you take this 10 and then you add it to the next one. You just remember it somewhere. So this variable maybe that you use here for the tens, you just initialize with 0 and then you put a formula that is going to always use it. And then when you have something bigger than 10, then you make it 1 and then, or whatever the value is, which probably should be 1. And then with the plus, that's all you can get. But what if it was a multiplication? Same idea. Now if you'd like to multiply two big numbers, it might run out of space in terms of the data types that you have. Yes.
So here the variable for the 10. Every time it's going to be 1.
Yeah, for the addition it's going to be 1. But for the multiplication it might be more. Okay, for the implementation though, now, there are different ways how to implement. I don't want to go into that. Now, I'll go back to that in a second. Now, this is how logically things work. When you push, pop, this is what they call the abstract stack, without any implementation. But what can we use to implement a stack? We could use an array on array list, because the array list allows to do that without us having to care about these growing or shrinking the array. And so it just adds things to, let's say, this pool, and then keeps adding. When I push, it's going to put it here. Then when I push again, it's going to put it at the next position, which is kind of easy for an array to add. But when you pop, you just need to pop the one again from the one that you have. So this is the array implementation, but we could also use the linked list implementation and the doubly linked list. This is an example of with that doubly linked list. When you push 10, you have just one node with 10, and then when you push again 5, so you have 10 and 5, but the head is going to point to the new one, which means we're going to always add to the head when we use doubly linked list as an implementation of the stack. And when we pop, we take from the head, we remove from the head, delete from head. It's like delete from head, and then it returns the value. And basically that's how this works. So I can implement it in both an array list or a linked list. Yes.
So it is like a single linked list.
Now this looks like a double linked list. You have two pointers.
Will it just do one direction? We add only to the head and we delete in the head.
Yeah.
It's like one direction.
I mean, what you're trying to say is that we don't need a double linked list to implement a stack. Well, yeah, we don't need, maybe, because all what happens to the head with a stack. So we don't really need we don't need to go back. Or do we? Well, so far we don't. Based on what we see, we just push to the head, which is add to the head, pop, delete from the head, and all the rest clear means empty the list. We don't care, we just empty everything. And that's it, we don't need that. So yes, you're right. The stacks, well, basically on Java 32 these are available. You can use those. There's a class called stack, java.util.stack, which has these methods. They call it peak, which is the equivalent of what the top element. It gives you the top element without removing it. It just returns the top element of the stack. This is what the peak means. And the pop, push, we know them. And they also have a search for an object. Return the position of some of them that you would like to find. And it's implemented using a double linked list, I think. Let me see. Now if we just let's find just a piece of code, whatever. I just would like to type java.util.stack, and I click on it so I can see its implementation. And you see stack extends vector, and then the vector is the superclass that extends an array list, an abstract list. No, it's an abstract list. This abstract that implements a list, and the navigator is still trying to find out. I don't know why, but it's kind of slow. I was trying to see index of remove. All right. So anyways, we have this push, pop, and peak. We just returns that without doing anything. Empty, just boolean, true or false, and the search is looking at it. And last index of, it seems that it's taking this as in some kind of an array, because an index is generally an array. So this seems to be a stack implementation. This stack is kind of a to be some kind of array implementation. So that's why the Java implementation of the stack is potentially fatal, because it's not really a stack. It's a structure with stack related methods, because they use just like some kind of an array. Another another type of application to the stack, why we need the stack, is something called the postfix expression. Have you ever heard about this thing? Postfix expressions? Well, this is what we used to do. Infix expression. An infix expression is the one that we've been using since we started programming. Which, when you would like to do something, you just put the operation between the numbers that you would like to get them involved in an operation, and use parentheses if you'd like to avoid having something that you don't want. The precedence rule, for example, if I don't have these parentheses, it will start by multiplying 9 by 2. But if I don't want to multiply 9 by 2, I would like to add them first, I need to put the parentheses. Now this is because of this infix, this is how it works. Now the postfix, there's another way where you can represent the exactly same expression, but this time with the possibility of never having to use any parentheses, because of the way you're going to write things. So it's not going to be confusing. You're going to write it in a way that is going to be not needing any parentheses. And that's the postfix expression. And this is an example of an infix, how you represent it in a postfix. So basically, if I divide 16 by 2, I don't write it like this. I write 16, 2, and divide. And then if I have this, 2 plus 14 multiplied by 5, I just say 2, 14 plus 5 multiply. Which, as you can see, I don't really need to put any parentheses, because basically I'm just saying the order where the operation should happen in the postfix. And that's the same thing for this one. Basically, this is the difference between this one and this one if you remove the parentheses. So now, because I'm going to start with this, right? I'm going to start with this first, then add the 2. So what happens is that I put the 2, I put the 14, the 5, I multiply. Well, multiplication needs only two numbers, so it means it's going to multiply the 5 multiplied by 14, which is going to be, what's 14 times 5? 70. And 70, I'm going to add plus, the plus is going to add the 70 to 2, which basically is going to be 72. This is the result of this. So that's the idea, that's how this works. The postfix allows us to not have to worry about the parentheses thing, and this is a different notation that exists. And what if you'd like to convert to that? There's a way how you can convert, but it's kind of a lot of details. Anyways, I'm not interested into doing that, but just you can have maybe some kind of idea about it, but I don't want to get into that for now. But that's something that is possible. So yes.
About the previous example.
Which one? This one?
The one with the 2 plus 14 divided by 5.
Yes.
How does it know that we want to multiply the 14 and the 5?
We would like to do what?
Multiply the 14 with the 5.
Because these operators, this multiplication, division, and plus, addition, they just work with two numbers. These are called binary operators, right? So we need only two numbers. So now if you give me 2, 5, 7, and you tell me plus, this plus doesn't mean add everything. It means just the previous two numbers, add them. So that's why this thing means, now I have 2, 14, 5, so this is what I have. And then I have the multiplication. Once I have an operation, I just look at the back and take the first two, and then I do the operation, which gives me, now this becomes a number.
Okay, then you add it.
And then when I have the plus, I'm just looking at two previous numbers, which is this is number and this other number, which means like we have 270, and then I have plus. So now this is going to add this 70 with the 2, and we get the result. You said something?
The result, after we take two numbers with operation, we take the result with the operation to the third number.
Yes, this
There
becomes
are
like a
four
number.
Third operation, there should be fourth number.
I don't understand the fourth number. What do you mean fourth number?
Operation.
Okay, so this becomes a number.
Yeah.
So this becomes the next step after this, which means do
Result.
70 and plus.
Yeah, we take the result, then the operation with the number before, and like this, we keep doing that until we finish all the operations.
Exactly. So that's what you mean with the number 4? That means the result of this is going to be your fourth number? Well, if that's what you mean, yes.
This not will be the fourth number. This will be the number with operation with the fourth number.
Which one is the fourth number? You get me confused every time you refer to.
Fourth number like 6, and we should add also.
You're talking about this
third
example?
operation.
Or this example?
The up example. We add
This one?
new operation.
Excuse me. Hold on, Qasim. Hold on. I'm asking you a question. You don't even listen to my question, and then you keep talking. Imagine if I was doing that. You'll be, kind of happy. Anyways, now what I'm saying. Now you said. Now I just wanted to ask a question. You're talking about this one?
Yes.
Yes, this one. Which one is the fourth number?
If we put the fourth number before 2.
Before 2, you put another number. 7, let's say.
7.
Okay.
Before it.
Before 2. Okay. All right. So now you get me following you. Now before 2, you put, let's say 7.
Yeah.
Okay.
And we put operation after plus.
After the plus.
Yeah, like minus.
Okay. So what this does, it's going to take these two.
The operation.
This becomes a number,
The result. And then
which is 70. So now I have 7, then 2, then 70 plus minus. Then
take the two
we take also this one,
and give us a result.
and
72.
this is going to be 72. So the result 72 minus.
And duplicate it.
And then this is going to do the operation again.
And keep that until
Yeah. The main idea behind this representation is that you don't need to put any parentheses at all, because you basically specify the order, the order where things should be executed. Yes. This one.
Minus multiplication plus.
Yes. If I do what?
Minus, multiply, then plus.
Multiply then plus? Because if you do minus here, that's fine. Alaikum salam. If you have, you mean you keep everything in their place, or you put them all at the end?
All in the end, minus,
Okay, so your question is, if I have 2, 6, 2, 5, 4, minus, plus, multiplication.
minus multiplication plus.
Minus multiplication plus. Okay, now it's going to be, let me erase this. Minus multiplication and then plus. And then plus. So let's. Now what is going to happen is that I have this. 5 minus 4, which is not here. So it's not going to be exactly the same. So it's going to be something different though. So I have 5 minus 4, that's give me 1. And then this 2 multiplied by 1, that's 2. And then 6 plus 2, that's 8. While here might be giving me, so this gives me 4 by 9, 62, 36. Yeah. So anyways, all these, I mean, stacks can be useful into using those things. Now, how those things work, like this is an example of how to evaluate a postfix expression using the stack. So you go through this. So you push, and then when you have the plus, you're going to be popping the 2, do the result, and you push it. So then, so this is, if you have an expression like this is what happens. You push these 2, then when you have this, you pop them, you do the calculation, and then you push the result. Then you have the numbers, you push them again. You have the operation, you pop 2, do the operation, push it again. You have another operation, pop 2, do the operation, and then you push the result, and that's going to be your result. So this is an example of this push pop thing. Okay. Now this is if you'd like to implement that, so you start with an empty stack, and then for each item in the expression, if it's a number, you push it. If it's not a number, then if it's an operator, you pop 2, you apply the operator, and then you push the result onto the stack, and then you keep going. So that's the main idea about this stack.